Hello, David Snowpeck here from Snowpeck Games, and this is part 5 in a tutorial series about implementing rollback netcode in a game built with the Godot game engine. In the last part, we added exploding bombs to our demo game. We covered spawning scenes as well as their despawning and respawning during rollback, and the network timer node from the Godot Rollback Netcode add-on. And today, we're going to be talking all about state. In the context of rollback netcode, state is the data that we save after every tick and then reload in order to perform a rollback. In the Godot Rollback Netcode add-on, it's the save state and load state virtual methods that are responsible for gathering the state from a node and then later reloading that state back into the node. As we previously discussed, we only send inputs to the other peers, not state. So our game logic must be deterministic. That means if two peers have the same starting state and apply the same inputs, they will get the exact same resulting state. Most netcode bugs when doing rollback netcode will be related to your game logic not always being deterministic, and this is what you'll spend most of your time debugging. But how do we even know there is a determinism issue? When you're playing, you can't generally see the other player's screens, and we're not sending the state. But we do send state hashes. Once we've finally generated input complete state for a given tick, we make a hash of the state. The state is input complete if it was based entirely on real input, with no predicted input mixed in. Since we store our state in a Godot dictionary, we can just call the hash method on the dictionary, which gives us a 32-bit integer. Two identical states will have identical hashes, and we send hashes to all the other peers, and they check it against the hash they calculated locally. When a client receives a hash from another peer that doesn't match the hash it calculated locally, we call that a state mismatch. If a certain number of mismatches happen in a row, this is a fatal state mismatch, and we kill the match. The exact number is configurable in project settings, so you can decide just how strict or lenient you want your game to be, keeping in mind that the most critical things to the outcome of the match, like the player health or the score, which are definitely being stored in state, will stay persistently out of sync every tick after they go out of sync, and only super minor things will fix themselves after a couple of ticks. So, what causes state mismatches? Generally, bugs in your game code. And I'm calling out your game code in particular because I've already had a few people contact me and say, the match is getting killed due to a fatal state mismatch. There must be a bug in the Godot Rollback Netcode library. But no, every single time when we've looked into it, it turned out to be a bug in their game code. It's not impossible that there could be a bug in the Godot Rollback Netcode add-on that could cause a state mismatch, but 99.9% of the time, this will be due to a bug in the specific game's code. Why? Because writing deterministic rollback-aware game code is hard. If you are making a game with rollback netcode, you are going to spend a ton of time debugging state mismatches in your game. In the course of converting Retro Tank Party to rollback netcode, I had to debug like 50 state mismatch bugs, and they were all in the game code for Retro Tank Party. For the most part, the Godot Rollback Netcode add-on is just moving the state around and doing bookkeeping on it. There are a couple of exceptions to that. For example, the rollback-aware nodes that it provides, like network timer that we used in the last video, those nodes are essentially gameplay code. They're in the network sync group. They implement the save state and load state virtual methods, just like your gameplay code does. So if there is a state mismatch bug in the Godot Rollback Netcode add-on, it'd most likely be in one of those nodes, but at this point, they are pretty well tested. So if you see a state mismatch bug, and you will probably see dozens of them in the course of making your game, it's most likely a bug in your game code where it's not deterministic, or not handling rollbacks correctly, or not following the rules of what can go in state, which we'll talk about later in the video. However, network issues can't cause state mismatches, and I've seen people head down this path and waste a ton of time. You can lose sync due to network issues. That's a legitimate thing, but the error you'll get won't be about a fatal state mismatch. The error will be unable to regain sync. The end result is the same. Your match will be killed, but the cause and the solution will be totally different. So keep an eye out for that. And we'll talk about dealing with network issues too in a future video. Anyway, let's go write some game code that causes a fatal state mismatch and see what happens. One quick note to folks who've been following along since the beginning of this series, you'll need to update to the latest version of the add-on because some of the stuff in this video wasn't present in earlier versions from a few weeks ago. So anyway, let's say we want to change our character movement to accelerate up to a top speed rather than just immediately moving at that top speed. So let's open up our player.gd. In our network process, you can see that we're moving a fixed 8 pixels per tick. Instead, let's add a speed variable at the top that starts at 0 and change the movement code to this. If the input vector is non-zero, we'll add 0.2 to the speed every tick, maxing out at a top speed of 8, and then use it to update our position. And if the input vector was 0, then we'll reset the speed back to 0, and that's it. Can you already see why this code is unsafe for rollback and will cause a state mismatch? I'll give you a hint. It's not the fact that we're using floating point math, although that is also a little problematic, but that's not going to be the problem for us here today. Of course, I'll tell you in the end and we'll fix the problem, but just as an exercise, see if you can figure it out before we get there. All right, let's run it. Make this one the server, this one the client. And once it gets going and I move around, you'll see that it starts out slowly and accelerates. You'll also notice that we aren't getting any state mismatches, and I told you that we would, right? Well, the reason is that no rollbacks are happening because both clients are running locally. Some problems won't happen until you have rollbacks, and some won't even happen until the clients are doing different numbers of rollbacks. So even introducing artificial latency might not show the problem if it's consistent, and both peers are doing the exact same number of rollbacks every tick. However, the Godot Rollback Netcode add-on gives us some debugging options that you should always be using if you are writing gameplay code to try and expose the issues right away when you are writing the code with the bug, rather than later when you'll also have to figure out which code is causing the problem. So we'll go to Project, Project Settings, and in the Network Rollback, we'll set the rollback ticks down here in the debug section, which will cause the game to always roll back at least this number of ticks every single frame. So let's set this to, say, 4. And we'll also set the random rollback tick setting, which will roll back a random number of ticks every frame up to the given maximum. So let's set this to 10. So this will cause the game, for debugging purposes, to always roll back between 4 and 10 ticks at minimum every single frame. Don't forget to disable this in the release version of your game, but you'll want to keep these settings turned on, maybe to different values, but always on when writing gameplay code. So let's try our game again with these new settings. I will set this one up as the server and this one as the client. And when I move the character around, let's open the debug overlay first. When I move the character around, we get loads of state mismatches, and the match gets killed with fatal sync error, fatal state mismatch. Now, we didn't change the code between the game working and crashing. That state mismatch bug was always there. It just didn't trigger until there were a variable number of rollbacks on each client. So our match got killed. The error is fatal state mismatch, but how do we even know what values in the state we're not matching? Neither peer actually has that data. They just have the state hashes to detect that there was a mismatch, but not the actual state data to compare and find the problem. To do that, our game needs to generate some log data that we can look at in the log inspector tool that comes with the Godot Rollback Netcode add-on. So let's add detailed logging to our game. We need to go over to the main.gd, and first we'll add a constant and a variable at the top. This is the directory to write the logs to. You can use any directory, but this is the default directory that the log inspector will look in first. And we have this variable to enable or disable logging. In a real game, this is something you'll probably want to have disabled by default, and a setting to allow players to enable it. The log files that get generated can actually get pretty massive. Retro Tank Party will generate hundreds of megabytes of log data for an average-sized match, so don't leave it always turned on for release. That's the main thing. Then, in response to the sync started signal, we'll add this code. If logging is enabled, we'll create the log directory if it doesn't exist, make a file name for the log, which includes a timestamp and the peer ID. If your game has some kind of match ID, you'll want to probably stick that in the file name too to help you group together all of the logs from a single match, because you'll actually need to load all of the log files from all of the peers into the log inspector in order to have all of the data you need to compare state and find mismatches. And in response to the sync stopped signal, we'll add this code that simply calls sync manager stop logging. So let's run it real quick and gather some logs. Make this one the server and this one the client again. Move around a little bit and we get a fatal state mismatch right away. So we'll exit out of here, go to Project, Tools, Log Inspector. The first thing we need to do is load all the log files from this match, so we'll click Add Log. This defaults to our local log directory. Since we ran both clients on this computer, the log files from both peers are already here. It's these two, this one for peer number 1, and this for the other peer. So we can just select both of them and click Open. If this was a real match, you'd have to ask all the other players in the match to send you their logs afterwards so that you could load all of them into Log Inspector. Anyway, here we see this colorful graph showing frame data from each peer, but this isn't what we're going to be looking at today. We'll talk about the frame viewer in a future video. There are two modes for the log inspector. This is the frame viewer, and then up top here, you can switch to the input state viewer. At the top right, you can see some basic info about the data that was loaded. We have 2 logs for these peer IDs with 94 ticks and 50 mismatches. We can click this next mismatch button to seek to the first mismatch. You'll see it takes us to tick number 43. In these top 2 panes, it shows the input data and any input mismatches on this tick. Input mismatches are super rare, but they are super critical if you manage to get any. They're usually caused by bugs in your getLocalInput or your message serializer class. These bottom 2 panes show the full state and any state mismatches on this tick. This is what we're looking for. We've got the server player and the client player, which are both storing their position in state. And the mismatch is that the other peer, the not host peer, has a different value for the X position. We can keep hitting next mismatch and see the 2 different values that the peers have for this piece of state. And you can see that it persists and actually tends to get worse. Yeah, here it's 10 pixels apart on this particular tick. So we know the issue is something with the player movement code. But wouldn't it be really cool to actually see the difference in state, like visually see the mismatch in the game? We don't really need it here because this game is so simple. It only has the 2 position vectors in state, and you could pretty easily visualize in your head what is happening here. But in a much more complex game with dozens or hundreds of values in state, it could be a lot harder to visualize what the state data actually means. In Retro Tank Party, for example, there can be hundreds of values in state in a single tick, depending on how many bullets are on screen and the different power-ups the players have. So I'm going to show off a really cool feature of the Log Inspector tool. It can actually show you a replay of the state from a particular tick from any of the peers that were in the match. But it requires a little bit of support from your game in order to work, so let's add that. First, we need to add a new autoload singleton. So we'll go to Project Settings, go to the Autoload tab, click Open, navigate to Add-ons, Godot Rollback Netcode, and the syncreplay.gd. Click Open, and then Add. So now you should see Sync Manager, Sync Debugger, and Sync Replay as autoload singletons. Then we will switch over to the General tab, back down to our network rollback settings. We need to set a replay match scene path. This will be the scene that the game loads when in replay mode. In my games, I usually have a match scene that runs the game when playing online for real, but that can also be reused for replay. But you could certainly make a unique scene just to run the replay. It depends on how you're organizing your game. In any case, for this very simple demo, we just use the same main.tscn, and this replay match scene method is a method on the scene that will be called to set up replay. And this default is fine. We'll just create a method with this name in our main.gd. We'll add it down here. And this method needs to take the peer ID that the replay will show, the rest of the peer IDs in the match, and a match info dictionary with info about how this match was configured so that you can configure the replay the same way. The match info actually comes from a second argument to sync manager start logging that we are not passing in. It would just go right here. It's just a dictionary that you can put arbitrary data into. In Retro Tank Party, we store like the game mode, the settings that were used, and the level that was played, but what you put in there will depend on the details of your game. So this could be like stage volcano. How do you spell volcano? Volcano, like that, I hope. But we don't actually need it for this super simple game. Every match is basically identical. We don't really need to do much setup except to simply hide some UI that we don't want to be available when running in replay mode, the connection panel, and the reset button, which we actually need to set up a reference to the reset button. There we go. And the error went away. One last thing, we need to make sure that we don't write more logs when we're in replay mode. So before we start logging over here, we can also check that sync replay.active is not set. So if logging is enabled and not sync replay active, then we will write a log. So that's all we need to do to support replay. Let's switch back to the log inspector. You can see that all of our data from before is still loaded, and up here in the replay toolbar, we click the launch button. Oop, I wanted that to appear down here. There we go. And when we increment the tick number here, you can see our player move around, showing the exact same state that we have recorded for this tick. And if we go to a tick with a mismatch on it, or I guess 82 has it, and we can switch which peer is being shown in the replay. So right now it's showing peer 1, we switch to this other peer, and you can see that the character is in a slightly different position. Again, this is not very useful for this super simple demo, but hopefully you can see how amazingly helpful this would be for a more complex game. Anyway, let's get back to our player script and see if we can figure out why the position doesn't match on each peer. Maybe you've guessed it. Were you able to figure it out in advance? The reason is this speed variable is essential to calculating our position here in network process, but we forgot to save it in state. So when the game rolled back to a previous state, it would reset the position here in load state, but the speed variable would still be set to whatever it was set to before, which could be anything. But if we add the speed variable to state and then load it again in load state, that should fix it. Let's try it out. This will be the server. This will be the client. We will turn on the debug overlay so we can be completely sure that there aren't any state mismatches. And when we move around, we can see that everything seems to be working now. We fixed it! This was a really simple example, of course, but I think it's a good one because it's an easy thing to forget. I've forgotten to add things to state a ton of times, but especially since the game may even work fine when you're testing locally because the problem only happens if there are rollbacks. So I've mentioned a couple of times in the series that there are rules about what can and cannot be put into state, and the time has finally come to discuss those rules. Rule number 1. Dictionaries and arrays must be duplicated both when putting them into state in save state and when pulling them out of state in load state. And this is because arrays and dictionaries are passed by reference. So if you put a dictionary into state and then continue to modify that dictionary, it will actually modify the state as well. And when you later go to load that state up again to perform a rollback, it will no longer be correct. So you'll need to write code like this. reference. We are calling the duplicate method when saving into state, and then calling it again when loading out of state. Rule number 2, nodes cannot, under any circumstances, ever be put into state. I mentioned this rule in the last video. Nodes have the same reference issue as arrays and dictionaries, but more than that, they are subject to spawning, despawning, and respawning, as well as reuse if you have that feature enabled. So that by the time you go to load them from state, they may no longer exist or be the node that you want, so instead, you should always store the node paths or other properties from the node. Number 3, no references or objects, and here I mean classes that descend from the classes named reference and object, unless you can duplicate them, like with arrays and dictionaries on both load state and save state, and you make a custom hash serializer that can convert them into something hashable. Otherwise, they are hashed based on their object ID, which will lead to an automatic state mismatch. We're not going to talk about making a custom hash serializer today. This video is long enough. We'll talk about that in a future video, but it's much the same as the way that we made a custom message serializer back in part 2. Rule number 4, you can actually put resources into state if they are loaded from a path. The hash serializer actually converts them into their path for hashing purposes, and they never change after having been loaded. Rule number 5. This is really more of a tip than a rule, but state keys can either be strings or integers, and this applies to input keys as well. Up until now, in this tutorial, we've always used strings as the keys into our state and input dictionaries, but integer keys with an enum to define all the possible keys can make it easier to avoid mistakes that come from mistyping a free-form string, and you can use autocomplete. So it's something worth considering, although it does make it harder to understand the state and input in the log inspector, because it'll just show the keys as numbers. In Retro Tank Party, I used integer keys for all the input dictionaries, but string keys for state. It's up to you. Rule number 6. This one is also more of a tip or a tool rather than a rule, but state or input keys that start with an underscore or are negative numbers if you're using integer keys will not be included in the hash, which may come in handy if you find yourself in a situation where you need something included in state or input, but you don't want it included in the hash. For example, in Retro Tank Party, there are a few asymmetric power-ups. For example, the invisibility power-up. When it's used, the player using it becomes invisible on all the other players' screens, but they remain visible on their own screen. If we put the visible property on the tank node into state, you'll get a state mismatch because the player that used the power-up would have true and all the other players would have false. But we need to store visible in state because it's something that we are toggling on and off. And if a rollback happens, we need to return it to its previous value. So this is a situation where you'd use a state key that starts with an underscore or that is a negative number. Whew. That was a lot of stuff today. I hope I managed to present it all clearly, but please let me know if you have any questions in the comments below or on the Snowpet Games Discord or wherever. Next time, we're going to talk about adding offline play to your game. It is possible to use the Godot Rollback Netcode add-on for playing your game offline as well, so that you can use the exact same gameplay code for both online and offline play, and we'll be setting that up for our demo game in the next video. So, please subscribe on YouTube, check out snowpetgames.com for a link to the Discord, and more information about me and my work. Thanks for watching. Bye-bye.